Max is walking on a mountain whose height is described by this function e to the x over y. So you give an x and a y, and the height, the altitude, is e to the x over y. Presently, Max is at the point 2, 1. In what direction should he travel to get down the mountain as quickly as possible? And so we're looking for a directional derivative to be minimized. And so that's done by taking the gradient of the function and taking -1 times it. That's the direction of the minimum directional derivative. The maximum directional derivative points in the direction of the gradient. The minimum directional derivative points in the direction opposite the gradient. What's the gradient? The gradient of a function is a vector field with its partial derivatives. The I component is the x partial. The j component is the y partial. And so the x partial is e to the x over y, and then we need to multiply by x over y's derivative with respect to x, 1 over y. The j component is the y partial, e to the x over y, and then we multiply by x over y's derivative with respect to y. And you keep the x, and 1 over y's derivative is -1 over y squared. So this is the gradient at any point. We're interested in the gradient at the point where he's at, 2, 1. Every x gets replaced by a 2. Every y gets replaced by a 1. That'll give you e to the 2 in the I component. And then in the j component, you'll have a -2 times e to the 2. This is your answer when you multiply it by a -1. And so what we get is -e squared and 2e squared. None of these answers have, none of these answers have any e squares in it. Any vector can be scaled by a multiplying factor. So we can factor out the e squared. We'd have the direction -1, 2. And so they just want the direction. There's infinitely many answers here. What we have here is e squared times the answer that they're looking for. That doesn't change the fact that it points in the same direction. And so we're going to go with the answer B here. -1 for I and 2 for j.